Hello, we are Enoc Lopez, Bryan Young, Krishna Paruchuri, and I am John Robinson. And today we're going to be discussing an introduction to TinyML. Slide. So, TinyML is a type of machine learning. It shrinks down machine learning networks to fit on tiny devices. Think low power microcontrollers. Think sensors. And it allows us to perform on-device analytics at the very edge of the cloud without relying on heavy, bulky remote machines. Slide.
Hi, I'm Krishna Paruchuri, and before going deep into the TinyML, I'll be talking about traditional IoT operation. The traditional IoT device will receive the data from the user and then transmit the data to the cloud, where the actual analytics on data are performed, and results are then transferred back to the user over the cloud. Slide. So as in the traditional IoT the data is stored in the servers over cloud somewhere else. So the privacy is not guaranteed and the latency is high since the model runs on the cloud and data doesn't have to be sent to the cloud for inference. So this increases the latency of the output. And the traditional transistor voltage technology for same transistors have been a particular level of voltage below which you cannot do meaningful computation. So signals become noise and outputs are unreliable. Slide. So coming to the TinyML overview, uh, it shrinks with the deep learning models to fit on tiny models, and it allows low power devices to run machine learning models. And as it runs on the edge of the cloud, on the edge, the data doesn't have to send to the server for inference, so it removes the dependency on the cloud. Slide. So why TinyML? It enables low latency, low power, and low bandwidth model inference at edge devices, while a standard consumer CPUs consume between 65 watts to 85 watts. This GPU consumes typically low power, that is 1,000 times less. So this enables the TinyML devices to run unplugged on batteries for weeks, months, or in some cases even years, while running ML applications on edge. Slide. So coming to the TinyML advantages, the data is local, so no privacy issues are taken into consideration. The low latency, since the model runs on the edge, the data doesn't have to be sent to the server for inference. This reduces the latency. The power consumption is very little. This enables to run without being charged for a really long time. And low bandwidth, as the data doesn't have to be sent to the server constantly, less internet bandwidth is used. Slide. Coming to the TensorFlow Lite, it is the framework that is used for generating the TensorFlow and machine learning algorithms that have been typically run in the cloud, scale them down to the level where you can run them on the microcontrollers. Coming to the software for TinyML, the authors of the original TinyML book have modified the TensorFlow Lite framework to run on embedded systems that only require as small as 10 kilobytes of memory available. This open source release has several TinyML projects embedded as examples to get started with, and the most popular ones are SparkFun Edge boards and the Arduino Nano 33. Also, Arduino has collaborated with Edge Impulse, a development platform that enables us to train, test, and deploy machine learning models on TinyML devices. Slide. Coming to the project flow, so we need to define the incident and then configure both hardware and software and acquire the data and train the data using the machine learning algorithms and generate the solution. Slide. Coming to the applications of TinyML. The voice commands. Smartphones actively listen to wake words like Hey Google or Hey Siri. Not surprisingly, the models that detect fake words are not run on the actual mobile CPU as it consumes lots of power and quickly drains the battery with continuous use. Instead, with TinyML, these models are run on specialized low power hardware inside the smartphone, which can run regularly and consume very little energy. The next one, high quality imagery. Microsatellite applications can high quality images and transfer them to Earth. These satellites feature fixed storage and can save a limited number of pictures. TinyML can help to capture pictures only when an object of interest is in sight. Equipment maintenance. TinyML can help to avoid downtime due to equipment failure by alerting technicians when equipment conditions go wrong as part of preventive maintenance. Retail stock. TinyML can help to monitor the stock of the products on shelves and send alerts when it's low. Crop management. For example, if we take a plant village, a research group developed a mobile app called NeuroAI that detects crop diseases in Africa. As it runs on the device, an internet connection not required, so it helps farmers who lives in remote places. Slide.
Hello, I'm Enoc Lopez, and I'll be going over some of the challenges and solutions that we've found with developing TinyML. Slide. There are some major challenges that have appeared with TinyML, just like with anything else. Many of them have to do with inherent properties of its design, just like with many other new technologies. And some of these challenges include fitting the neural network models into hardware with smaller constraints of resources, such as, something as small as a microcontroller, of course, doesn't have as many resources and power as, like a larger CPU and many other devices that we have. And also, problems with optimization of cross performance happen with TinyML, such as when you have such a small and efficient program, it gets really good at one thing, but it gets a lot harder to use that across to use the same machine learning algorithm for multiple different uses because you have to get more and more niche as you make it more efficient and you compress it. More power efficiency as well as quicker computations are also needed with these smaller chips, with these smaller microcontrollers. And also, another challenge is optimization to embedded chips are necessary. You usually need your hardware to be very optimized and very specific for the task. Slide. Here are some of the solutions that we found for for these issues with TinyML. Slide. We've been furthering the advancement with TinyML and finding solutions to these issues. Although there's not solutions to all of the challenges, but many of the new advancements that we've been improving to be able to develop TinyML further we've gotten smaller and faster chip solutions with better power. We've designed embedded systems that are better optimized for running TinyML and the algorithms, and also that increase the efficiency because they're made specifically for them. And also, another important aspect has been balancing between power consumption and the accuracy and speed of processing, because you must be very because these systems use a lot less power, and the point of them is using a lot less power and less resources. Is You need to make sure that they're very efficient, and also you want to try to make them as efficient as possible without sacrificing too much on accuracy, but still having a fairly useful amount of speed of processing. Also, better compression methods have been found for light and useful models on these embedded devices. Slide. This is one of the solutions that we found for some of these issues with TinyML that have helped with the development of it. Model compression algorithms we've used to make these models smaller and smaller to be able to fit them on these devices. And so, with the limited resources on these microcontrollers, we've had to make the model compression better and better. We have really powerful neural networks right now, but the models can't be run directly on an embedded device with such a small amount of memory. Therefore, a lot of these advancements have dramatically improved the development of TinyML. And so there have been many different techniques that have been combined in order to make TinyML as efficient, and the algorithms that we develop on it as efficient and as small as possible. Things between machine learning, signal processing, optimization, and even computer architecture. Model compression algorithms also help reduce the model size and minimize the accuracy loss as well with the models that we use. And one of the compression methods of compression, also the application of Huffman coding applied to these algorithms, also results in up to 30% memory space. So we've come a very long way in being able to develop this. Slide. This is another solution and also has to do with compression, and this is a certain compression method that we've developed that to date in technology, which is knowledge distillation, which it's another method of model compression, and in which includes a teacher model that's transferred to a smaller student model. The student model is a smaller version of the parent model with training using a softmax input from the parent, as well as a penalized function to make sure that it's efficient. The method is most used when there's a small amount of data and also when it's very necessary to have a large amount of efficiency improvement with the algorithm. Slide. This is another solution as well, which is outside training, in which we know that inside the embedded devices, resources are very limited, and microcontrollers today just can't run model training on them yet. But we can run the training models on the cloud or on a device much more well equipped, and then after the model is trained, compress it and then put it on the embedded device. And then in the end, we can update it frequently as our progress in TinyML increases, because there's a lot of people are expecting that TinyML is going to just keep exponentially increasing in use as we get more use out of it, we keep developing it, and we get more and more microcontrollers out there using TinyML. Slide. Solution 3, selecting models. Of course, not every algorithm works for every problem. In the same way, not every machine learning algorithm is going to work the best for every application. Therefore, selecting a neural network model is very important for it to work for the application at hand. And so maximizing space efficiency to be able to function within the resource constraints of the embedded system is very important. Slide.
So how does TinyML work? Well, as mentioned previously, neural networks have been able to achieve dramatic accuracy improvements over the past couple of years, thanks to large models with millions of parameters and the availability of high computing resources. However, these models can't be directly deployed to the embedded devices with low memory. That's where TinyML works. See, over the past few years, significant progress has been achieved in model compression techniques. One such is the pipeline processing architecture shown here. Now, it probably looks like a lot of jargon and a lot of data being thrown at you really fast. So let's break it down just a little bit. In this compression pipeline, there are three main stages. Stage 1, pruning. In this stage, we reduce the number of weights by approximately 10 times. Stage 2, quantization. We cluster those weights, the ones that are left, into a code book, and then retrain the neural network on the code book over and over again, further improving the compression by approximately 30 times. And finally, after pruning and quantization, we compress further with Huffman coding, which is a process that will be described a little bit in just a moment. But starting back at stage 1, model pruning. This stage aims to reduce the number of connections in the neural network model. It prunes non-informative weights based on some loss function. It starts with regular network training, where connections between the layers are learned. It's followed by the pruning of small weight connections, usually using a fixed threshold value. Then, the network can be retrained to learn the final weights of the remaining connections yet again. In the second stage, the parameter quantization, this stage aims to reduce the network size by reducing the number of bits needed to represent each weight. Again, it's normally based off of a set threshold, or maybe even searching for a min-max range that they could alter via each search. It then can decide the best ways to allocate bits for the integer part of the weights to cover the whole quantization range. Then, it executes a chosen algorithm to allocate the bits based off of the data that they have. And in the third step, network compression with Huffman coding. In this step, compression of network coefficients is done using lossless coding, much like ASCII coding, where it uses variable length code words to encode source symbols, such as where more common symbols can be represented with fewer bits. By the time this stage is completed, hopefully the data will be compressed 35 times to maybe 49 times its original value, while keeping complete and total accuracy.
So in conclusion, with TinyML, machine learning is no longer the domain of beefy cloud machines. This opens up huge possibilities for things like intelligent sensor networks, and so on. And TinyML has further driven advances in other areas, such as model compression in particular. Slide. So, what can we expect to see in the future? In broad terms, we can expect to see greater automation, which is driven by intelligent sensors, which are themselves used to power distributed decision-making processes. On the flip side, as we continue to push data to the edge and process it where it's generated, we can expect to see far less operational latency, far less data movement, and again, far less reliance on remote computation. Slide.